Implemented here is a spell checker for fake news detection. The motivation behind this project lies in the idea that in a world so interconnected by the internet, it is of utmost importance to be able to accurately identify and get rid of fake news that is disseminated through the online medium. What we typically notice with fake news websites, contrary to what we'll notice with real news websites, take New York Times or CNN or Fox News, for example, the New York Times, Fox News, and CNN websites, they will have a much more robust set of editors that are able to make sure that the work they put out is reputable, and to also make sure that it's grammatically correct, spelled properly. With fake news websites, what we typically see is a lot of spelling errors in their work, and this is also said in my report with citations as well. What's important to note here is that if we can exploit spelling errors in websites, and with a reasonable degree of confidence determine that a website contains fake news or not, we're able to pull it off the internet and make sure that such news is not disseminated. So this code right here does exactly that. We're going to walk through it. So first we import all our necessary packages. And then what we're going to do is we're going to download a corpus of words. These words are going to contain the correct spellings of the words that we mean to use. Say for example, I use the sentence, I want to take my cog on a walk. I mean dog. So I type in COG, but I want to put DOG. So the words is going to contain the variable words right here. That's going to contain, the corpus words right here is going to contain the word dog. So it's going to contain the correctly spelled words, which we'll use to compare with our misspelled words. So that's already there. Next, what we're going to do is we're going to read from our true.csv file. The true.csv file is a CSV file containing a list of multiple articles. These are all real news articles, all with no grammatical mistakes, no errors. This is what we're going to train our data on. What's also important to note here is we append start and end tokens to the end of sentences. The reason this is important is to uphold probabilistic consistency. Say for example, I use the two sentences, I go to the store, I buy an apple. I will typically not come after store, because if I combine the two sentences, I go to the store, I buy an apple, I comes after store. So to get rid of these logical inconsistencies, what we do is we append start and end tokens to the end of sentences to make sure that our probabilities are more accurate. So that's what's done here. This length of words tells us how many words, including our start and end tokens, we have in our training corpus, which is a relatively large size for our purposes, but in the world of natural language processing, we would need something on a much larger magnitude. Next, just for viewing purposes, we can look at a sample article. So what it is it's the publisher and then a sample article. This is about transgender people being allowed to enlist in the US military. So this is what one sample article looks like. Next, what we're going to do is we're going to create our bigrams. Bigrams are groupings of two words. Take the sentence, I am feeling sick today. Our bigrams would be I am feeling sick today. So the by prefix means two. So a bigram is just a grouping of two consecutive words in a sentence. Where we're going to use bigrams will be discussed soon, but first we have to create them. So what we do is we take the corpus of words and we create a bigram frequency dictionary, a word frequency dictionary, and then a list of all the bigrams. And we basically just append every single possible bigram to the list. So that's what's done here. So we create our bigrams, that's our function, and now we actually create them. So it takes a little while because there's multiple words, a lot of words in our training corpus. Once that's created, we have to calculate our bigram probabilities. So the way this works is we first use Laplace smoothing, +1 smoothing. We also use log probabilities to ensure that when the probabilities get super small, we don't lose the probabilities due to rounding errors. So what we do is we take every single bigram in the list of bigrams, and we check how many times that bigram occurs over the total amount of words that occurs, or over the total amount of the first word in the bigram that occurs. So this is going to give us our probability of that one bigram showing up. So we're going to return that, and then we're going to calculate those bigram probabilities. So what this is doing here is it's checking the frequency of every single bigram in our list of articles. Next, we create a second function, calculate unknown bigrams probability for a certain bigram. The reason this is important is, let's say in our test set, we have a bigram that doesn't show up in our training set. We can take a random bigram. We can take mouse keyboard, for example. That may actually show up grammatically correct in our test set, but it's not in our training set for whatever the reason is. So what we do is we check and make sure that every single bigram is included. If it's not, then we add it and we recalculate the probability. We give it a frequency of 1 because this is the 0 frequency plus 1 smoothing, and then we add the amount of words onto the denominator to ensure that we're getting a consistent probability and we're not running into 0 probabilities. So as an example, we can look at these two functions and how they run. So if we create a bad bigram, Trump Donald, that wouldn't make sense. What would make more sense is Donald Trump. Trump will come after Donald. Donald will come before Trump, not the other way around. So what we do is we check if bad bigram is not in bigrams, which we know it's not in there, but we're just going to test it. We're going to calculate the unknown probability, we're going to print that probability, and then we're going to calculate the bigram probability of Donald Trump. We're going to print that as well. So we see two different probabilities here. One probability, this negative 15.969 probability, log probability, it's important to note, is for the bad bigram, and negative 7.203 is for the good bigram. The good bigram probability is significantly larger than the bad bigram probability, as we would imagine, because Donald Trump is way more likely to show up than Trump Donald. This is just as a sanity check, and more so to conceptually understand the way that these two functions work. Next, this is just to see what our most common bigrams are. So we're going to print the top 25 bigrams. So our most common bigram is of the, which makes sense. Of the is a very common term. And then in our training corpus, we have these as the top 25 bigrams. So from the, said the, in a, these are our most common. This is where we begin to test the model. Let's take the following sentence. The former president, Donald Trump, lives in the White House. We know that this Trump is supposed to be Trump. This F should be a T. So let's run it through our pipeline. So we create the original sentence. Next, what we have to do is format our sentence. We need to get rid of any punctuation, and we need to lowercase every single word because the words in our vocabulary are all lowercase. So we're going to format our sentence, and this is the sentence we get. The former president, Donald Trump, lived in the White House. Next, what we're going to do is we're going to split the sentence at every single space and feed it in as a list. We're going to call that sentence words, and we're going to get our bigrams, our frequencies, and our bigram frequencies. Our word frequencies and our bigram frequencies. So we feed that in. We're going to print our bigrams. So the former president, President Donald Trump, as we would expect. We're going to print the frequency of every single word. We're also going to print the frequency of every single bigram, which is exactly what we need. Next, what we're going to do is we're going to calculate the bigram probabilities. We're going to calculate the probability of each one of these bigrams showing up in the original training set. So in our training set, that contains the list of all the articles. This right here, we're going to check the probability of every single bigram showing up. And again, if it's not in the bigram probabilities, we're going to add it. We calculate the probabilities, and these are the probabilities we get. So log probabilities. So negative 8.9, negative 8.9, negative 7.3-ish. Here, what we notice here is negative 15.966, and then negative 15.96495. So these are significantly smaller probabilities, which we would expect because Donald Trump and Trump lived is not a common term. Trump is not a word. So this is logically consistent. Next, what we do is we calculate our smallest probability. This is going to say which one of these bigrams contains the smallest probability, and as expected, we get Donald Trump. Then what we're going to do is we're going to print the two smallest. So we know our smallest probability occurs with Donald Trump, but what are the two smallest bigrams? Donald Trump and Trump lived. Now the way this is formatted is it contains the first word, the middle word, and the last word. We know the middle word is always going to be the incorrectly spelled word because that is the word included in both bigrams with the smallest probability. So we know here that our incorrect word is Trump. It can be accessed either way. This is just array accessing. We print our incorrect word Trump as desired. Next, what we do is we're going to turn our English word set into a list. This is going to be important in determining where the correctly spelled words are. So just as a little introduction, these are some words that are in and not in the English word set. So hello is included, Trump is included, Clinton and Obama are not included, jump is included, esoteric is included. These are just random words chosen. Next, what we do here is we create a minimum edit distance table. What a Levenstein minimum edit distance table. What this table does is it tells us the minimum edit distance between two separate words. This is important because we're going to be able to figure out what the most likely word that's supposed to be used, what that actually is going to be. So we use this minimum edit distance table. We use a tabular approach, and Levenstein defines substitutions as with a cost of 2, and then insertions and deletions with a cost of 1. So create that minimum edit distance table. And just to see, we can check the minimum edit distance between apple and trample. For example, that's going to give us 4. We're also going to print the length of English words. We have 25,487 words included in this corpus right here. Next, what we're going to do is we're going to calculate the minimum edit distance table. We're going to calculate the words with the minimum edit distance to our incorrect word from our list of words. And these are the words we get. We calculate the top 20. So we get rump, trump, crump, fum, grump, form. These are all the different words that we get. Now that we have a potential list of words that the user could have meant to have typed, we assume that there's a typo included, therefore we're going to find the word that is closest to what they wanted. What we do is we create the new bigrams, and then again we run those probabilities and figure out what gives us the highest. So we create the list of probabilities, we create the new bigrams, calculate the new bigram probabilities, figure out the largest probability. So we do that here, and we get this. Donald Trump would have the highest bigram probability at negative 7.20. Therefore, our new word that we want is Trump. To make it interactive, we can run this, and it says, former President Donald Trump lived in the White House. Did you mean to replace Trump with Trump? We typed, yes, we did. And then our updated sentence, the former President Donald Trump lived in the White House. Now, implemented here is a tree. A tree is used to make searching faster. And we use, again, a Levenshtein distance here, but this is based on recursion. And the way a tree works is when you run a Levenshtein distance table, if you add a suffix onto the end of a word, say you change dog to dogs or run to running, when you add a suffix, the Levenshtein distance will only change at the bottom row, which is really all you need. Because if we notice here in our minimum edit distance table, we always return the element at the bottom rightmost corner of our table. So that's exactly what we do here. Instead, we just use a recursive approach to not have to recreate the table every single time. We use a tree structure, and that just inserts nodes corresponding to every single letter that has already been added. So it's much more efficient. Now, the reason this was just done as a thought experiment, and the reason this is important, is this will let us search through the list of words significantly faster than using an iterative approach as we use above. The reason this is important is if we actually had a much larger data set, what we could do is use a tree to search through and then give us the most common word, the closest edit distance words. This would be, again, more important if we had a larger data set. Unfortunately, we do not, so for these purposes, we're just going to be using an iterative approach. But just to see it in action, this is just a tree to search faster. And what we notice here is to figure out the words that have a minimum edit distance of 3 or less to from. These are all the different words, and all it took was 1.5994 seconds. So this is clearly more efficient. Now, just as a pipeline, just to see other sentences in action, let's replace this sentence right here. The former President Donald Trump lived in the White House. Let's change this to the New York Times is a great. Let's change it to freight paper. So again, we know our typo is freight, but we can just run it through. So we're going to run through. We're going to format our sentence. We're going to get our bigrams. We're going to get our smallest probability, which we should get a freight, which is exactly what we want. And then again, a freight paper. This middle word is the incorrect one. We got our incorrect word as freight. Okay, we can just run through this again. This isn't going to change. Get our minimum edit distances exactly as desired. Okay, so right here we're going to get the closest words to it, and then we're going to get great. Great is going to be returned as our correct word. So we can run this just for interaction. Do I mean to replace freight with great? Yes, as desired. We can try one more. Let's change this sentence right here to running for precedent. Precedent is an onerous task. We can make that sentence. So here's our typo right here. Run it through the pipeline again. It's doing the exact same thing. So it tells us our incorrect word is precedent, which is what we would like. Okay, and then we're going to run through, calculate our probabilities, our distances. Then again, we're going to run it again and figure out that president would be the most likely word. And for interaction, yes, we did. Perfect. Running for president is an onerous task. So the algorithm works and it gives us the necessary probabilities. Let's say, for example, that, or actually, we can just put in a sentence that we know is not going to work. So let's say I use the sentence, I work as a reporter for an international news organization. So we know our typo here is reporter. It should be reporter. Let's run it through and see what happens. So we run through, get our probabilities, and it tells us our incorrect word is reporter, as desired. That's perfect. That is our incorrect word. Great. Now let's run through and figure out what should the substitution word be. What do we actually want? It gives us the word part. That's not correct. So it says, do you mean to replace reporter with part? We put no, and it says we could not find a suitable change. So what's important to note here is our algorithm did not return the correct word. Why is that? Well, let's try something. Let's first make sure that the word reporter is even in the corpus. So we can do the exact same thing. Print reporter in English words. I'm sorry, what is the list called? It's called English words. Oh, typo. False. This is important to note. Reporter is not in the corpus. That's why it did not return the correct word. So a problem that we're going to run into is a lack of training data. A lack of data generally makes it difficult for this algorithm to run. It successfully did what it was supposed to do, which is identify that reporter is the misspelled word. Reporter is the misspelled word. It doesn't give us the correct word. It doesn't give us reporter back because that is false. Reporter is not in the list. So the moral of the story here is what we would need to make this a more efficient algorithm, a more robust algorithm per se, would just be more data. It does what it's supposed to do. It uses Bayesian probabilities and Bayesian probabilities along with Laplacian smoothing to make sure that we're able to identify misspelled words. Now the idea here is to be able to scrape thousands of websites, set some value, which could be done through machine learning, naive Bayes, logistic regression, set some boundary value to see what kind of amount of incorrect words would be in a typical article. Is it less than 1%, less than 2%, less than 0.5%? What would that boundary be? Use machine learning algorithms to determine that value. Then parse through every single website and parse through every single article on that website, determine the amount of misspelled words to figure out what all is misspelled, and then be able to accurately classify a website as containing fake news or not. This is crucial in our days because there's a lot of fake news circulating around the world, and I think it's a fascinating idea to be able to solve it all while using natural language processing and Bayesian probabilities. Thank you.